Section 10.18 Warps and Morphs. Let the three vertices of a triangle be given by the three non-collinear points v1, v2, and v3, as in this figure. We will call this triangle the begin triangle, because what we're going to do is we're going to take the triangle and we're going to warp it into a different triangle by transforming the points v1, v2, and v3, because if v is any point inside of the triangle, then there are unique constants c1 and c2 such that v minus v3 is equal to c1 times v1 minus v3 plus c2 times v2 minus v3. If we set c3 equal to 1 minus c1 minus c2, then we can rewrite this equation as v equals some linear combination of v1, v2, and v3, where the constants add up to 1. So any point inside of the triangle can be written as a linear combination of the endpoints of the triangle. So we'll warp the entire triangle, and we'll be able to rewrite the points inside of the new triangle, which this is the begin triangle, the new one will be the end triangle, and we'll do that by taking advantage of this property. We say that v is a convex combination of the vectors v1, v2, and v3 if these equations are satisfied, and in addition, the coefficients c1, c2, and c3 are non-negative. It can be shown that v lies in the triangle determined by these v1, v2, v3 vertices if and only if it is a convex combination of those three vectors. Let's do an example. How about we determine whether the vector v is a convex combination of the vectors v1, v2, and v3. So let's start with v equals 3, 3. Remember, to be a convex combination, we need v to be equal to some constant c1 times v1 plus c2 times v2 plus c3 times v3, where c1 plus c2 plus c3 equals 1. So c1 is unknown, but v1 is given to us as the vector 1, 1. And then we have to add that to c2 times the vector v2, which is given as 3, 5, and add that to c3 times 4, 2, and then some of these constants c1, c2, c3 have to give us the vector 3, 3 that we want. That's our vector v. So I just moved it to the other side. Now let's solve for c1, c2, and c3. So I'll write the matrix 1, 3, 4 by just reading off the first entry for each of the vectors, and then my second row will be 1, 5, 2, and then I'll just set the last row to be all 1s. So I'll multiply that by c1, c2, c3, and set it equal to 3, 3, 1. This way I have a three-dimensional way to write it. So let's reduce the augmented matrix. So the top row will be 1, 3, 4, 3. I can leave because I have a leading 1, but underneath I want to get 0, so I'll subtract from the top row from the other two rows, and I'll get 0, 2, minus 2, 0, and 0, minus 2, minus 3, minus 2. Okay, let's keep going. How about we get a leading 1 over here? So I'll divide by 2, and at the same time I'll subtract that from the top row and the bottom row, suitable multiples, in order to get zeros there also. So I'll end up with 1, 0, 7, 3 in the top row, 0, 1, minus 1, 0, dividing it by 2. So you just take 3 times that and subtract from the top. And then, again, add to the bottom to get 0, 0, minus 5, minus 2. Almost done. We just have to get this minus 5 to be a 1, so we'll divide by minus 5, and then add and subtract suitable multiples to get zeros above it. So we'll end up with 1, 0, 0, 1/5, 0, 1, 0, 2/5, 0, 0, 1, 2/5. Okay, cool. So we found C1 equal to 1/5, C2 equal to 2/5, and C3 equal to 2/5. So all of these are greater than or equal to 0. So that means that V is in fact a convex combination of V1, V2, V3. Notice that these add up to 1 because we forced them to. We took C1 plus C2 plus 3 and we set it equal to 1. Let's do that again for the second example, different vectors this time. So we'll have C1 times 1, 1 plus C2 times 3, 5 and C3 times 4, 2. Set that equal to 2, 4. Okay, let's see if we can find C1, C2, and C3. So this time our matrix is 1, 3, 4, 1, 5, 2, 1, 1, 1, same as it was last time, and C1, C2, C3, but this time we are looking for a different vector V. That's 2, 4, so we'll write 2, 4, 1. And we'll reduce to get 1, 3, 4, 2 in the top row, and then get zeros underneath. So 0, 2, minus 2, 2, 0, minus 2, minus 3, minus 1, and reduce further, get 1, 0, 7, minus 1, 0, 1, minus 1, 1, 0, 0, minus 5, 1. So we have leading 1 there now, and let's get this minus 5 to be a 1, so we will get 1, 0, 0, 2/5, 0, 1, 0, 4/5, and 0, 0, 1, minus 1/5. And you can already see that there's a problem right there. We have C3 equal to minus 1/5, which is negative. So that means that V is not a convex combination of V1, V2, V3. All the constants have to be positive. Let's try another example. In this case, we want to solve for C1 times 3, 3 plus C2 times minus 2, minus 2 plus C3 times 3, 0. Setting that equal to 0, 0 vector. Okay, great. So we have our matrix reading off the top row, 3, minus 2, 3, 3, minus 2, 0 for the second row, and 1, 1, 1 for our last row. Multiplying that by C1, C2, C3, and setting that equal to 0, 0, 1. So we get the reduced matrix. Let's see, 1, 1, 1 by dividing by 3 on top, and then subtracting to get 0, minus 5, minus 3, minus 3, and 0, minus 5, 0, minus 3. Further reduce to get 1, 0, 2/5, 2/5, 0, 1, 3/5, 3/5, 0, 0, 3, 0, which then becomes 1, 0, 0, 0, 1, 0, 0, 0, 1, where the top coefficient is 2/5, then 3/5, and then 0. And 0 is fine for a coefficient. It just has to be greater than or equal to 0. So we could just set C1 equal to 2/5, C2 equal to 3/5, C3 equal to 0. They're all greater than or equal to 0, so that means that V is in fact a convex combination of V1, V2, and V3. Okay, last one. Let's set C1 times 3, 3 plus C2 times -2, -2 plus C3 times 3, 0 equal to 1, 0. For our top row, we get 3 -2, 3, 3 -2, 0 for second, 1, 1, 1, same matrix as in C. We have C1, C2, C3 again. And we set that equal to 1, 0, 1 this time. So we have a reduced matrix 1, 1, 1, 0, -5, -3, -3, 0, -5, 0, -2, which becomes 1, 0, 2/5, 2/5, 0, 1, 3/5, 3/5, 0, 0, 3, 1. And we get 1, 0, 0, 0, 1, 0, 0, 0, 1, where the first coefficient is 4/15, the second is 2/5, and the third is 1/3. So it ended up working out. C1 is equal to 4/15, C2 is equal to 2/5, and C3 is equal to 1/3. They're all greater than or equal to 0. So V is a convex combination of V1, V2, V3. Okay, so now that we know how to identify if points are convex combinations, we can identify if they're actually in the triangle. Let's actually do some warps. So given 3 non-collinear points, W1, W2, and W3 of an N triangle, in this figure, there is a unique affine transformation that maps V1 to W1, V2 to W2, and V3 to W3. By that, we mean that there is a unique 2x2 invertible matrix M and a unique vector B, such that each of the W's is M times each of the V's plus B. Moreover, it can be shown that the image W of the vector V under this affine transformation is a linear combination of the W's, where you use the same C1, C2, and C3 as you did before. To each point in the begin triangle, we assign a gray level, say 0 for white and 100 for black, with any other gray level lying between 0 and 100. In particular, let a scalar valued function ρ0, called the picture density of the begin triangle, be defined so that ρ0 of v is the grade level at the point v in the begin triangle. We can now define a picture in the end triangle called a warp of the original picture, with the picture density ρ1 by defining the grade level at the point w within the end triangle to be the grade level of the point v in the begin triangle that maps onto w. In equation form, the picture density ρ1 is determined by ρ0 of c1v1 plus c2v2 plus c3v3. Suppose we are given a picture contained within some rectangular region of the plane. We choose endpoints v1 through vn within the rectangle, which we call vertex points, so that they fall on key elements or features of the picture we wish to warp. Once the vertex points are chosen, we complete a triangulation of the region. So if we can map the triangles, we can map any region. A time-varying warp is a set of warps generated when the vertex points of a begin figure are moved continually in time from their original positions to specified pion positions. We won't do an example of that, but you can kind of imagine it. Time-varying morph can be described as a blending of the two time-varying warps of two different pictures using two triangulations that match corresponding features in the two pictures. We'll do just the maps between the triangles. So let's find the 2x2 matrix M and two-dimensional vector B that define the unified transformation that maps the three vectors v1, v2, and v3 to the three vectors w1, w2, and w3. We'll do this by setting up a system of 6 linear equations for the 4 entries in the matrix M and the 2 entries of the vector B. Okay, we'll set our matrix M equal to the arbitrary matrix M11, M21, M12, and M22, and we'll solve for each of those, and then we'll set B equal to the vector b1, b2, and we'll solve for b1, b2. So we know that M times each of the vertices, the vertex vectors, vi, plus B has to be equal to each of the wi vertices. Okay, so that means for I equals 1, we have M11 plus M12 plus B1 equal to the first W entry, 4. And we have M21, M22 plus B2 equal to 3. Right? We also have, for I equals 2, M11 plus, oh, well, actually, there's a coefficient, right? Because we have to multiply by each of the V's. For the first set, we had 1, 1, so that made it pretty easy because each of these was 1. But in this case, we're looking at V2, so we have to multiply by 2, 3, so we should have 2M11 plus 3M12 plus B1 equals the first entry in W2, 9. And we should have 2M21 plus 3M22 plus B2 equal to 5. Last but not least, for I equals 3, we have 2M11 plus 1 for M12 plus B1 equal to 5, and we have 2M21 plus M22 plus B2 equal to 3. So that gives us a matrix of 1, 1, 1, just by reading off these coefficients. For M11, 2, 3, 1 for these coefficients, and then 2, 1, 1 for the last ones. So that's just taking the first of each of these rows. Okay, so that'll give me M11, M12, and B1 if I set it equal to 4, 9, and 5. And then for M21, M22, and B2, we'll take the second rows. So that'll be 1, 1, 1, 2, 3, 1, and 2, 1, 1. Right? Just by getting the coefficients and multiply by M21, M22, and B2. Setting them equal to 3, 5, 3. Okay, let's reduce the first one first, this one. So we'll get 1, 1, 1, 4, and we'll get zeros underneath leading 1, so 0, 1, minus 1, 1 by subtracting the top row, 0, minus 1, minus 1, minus 3, which becomes 1, 0, 2, 3, and then 0, 1, minus 1, 1, and then 0, 0, minus 2, minus 2, and be further reduced to 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 1, giving us M1, 1 equal to 1, M1, 2 equal to 2, and B1 equal to 1. So that means we can start writing our matrix M. We have 1, 2, and we don't know what the bottom two entries are yet, and we have B equal to 1 something. So let's reduce the second matrix now. We have 1, 1, 1, 3, and then underneath we can get 0, 1, minus 1, minus 1, 0, minus 1, minus 1, minus 3, becomes 0, 0, or actually, it's mistakes, 1, 0, 2, 4, 0, 0's in the bottom, 0, 1, minus 1, minus 1, 0, 0, minus 2, minus 4. Okay, so we'll end up with 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 2, giving us M2, 1 equal to 0, M2, 2 equal to 1, and B2 equal to 2. So we can finish our matrix M by putting in a 0, 1, and our vector B by putting in 2. And we found M and B. Let's do another example. How about if we have these vectors, V's and W's? So then we do the same thing as before. We write out this system. All we have to do is change the coefficients of the M's a little bit and change what they equal. So we'll just get slightly different matrices over here, but by adapting it similarly to the way we did here, we'll just replace all of these numbers with the corresponding numbers here, so I won't rewrite this again. Instead, I'll write what the matrices end up as. So we have minus 2, 2, 1, 0, 0, 1, 2, 1, 1, for the matrix that we multiply by M11, M12, and B1. And we have minus 2, 2, 1, 0, 0, 1, 2, 1, 1, times M21, M22, B2, First one is equal to minus 8, 0, 5, right, picking up the W's, and the second one gives us 1, 1, 4. Okay, so solving the top one, we get 1 minus half, 4, dividing by 2, 0, 3, 2, minus 3. We're just swapping these rows so that we have the this one on the bottom. So we'll have 0, 0, 1, 0. And that becomes 1, 0, 1, 6, 3, 0, 1, 2 thirds, minus 1, 0, 0, 1, 0. Which further reduces to 1, 0, 0, 3, 0, 1, 0, minus 1, 0, 0, 1, 0. Giving us m, 1, 1 equal to 3, m, 1, 2 equal to minus 1, and b1 equal to 0. For the second matrix, 1 minus 1 minus a half after dividing, and then 0, 3, 2, 5, 0, 0, 1, 1. After swapping, becomes 1, 0, 1, 6, 7, 6, 0, 1, 2 thirds, 5 thirds, 0, 0, 1, 1. We get 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1. So m21 equals 1, m22 equals 1, and b2 equals 1, giving us m equal to 3 minus 1, 1, 1, and b equal to 0, 1. Let's do another one. So we'll have this time the matrix minus 2, 1, 1, 3, 5, 1, 1, 0, 1 times m11, m12, b1 equal to 0, 5, 3. And now for the second rows, minus 2, 1, 1, 3, 5, 1, 1, 0, 1 times m21, m22, b2 equal to minus 2, 2, minus 3. Okay, solving the top one, we get 1, 0, 1, 3, 0, 1, 3, 6, 0, 5, minus 2, minus 4, reducing to 1, 0, 1, 3, 0, 1, 3, 6, 0, 0, minus 17, minus 34, which becomes 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 2, giving us m11 equal to 1, m12 equal to 0, and b1 equal to 2. The second matrix reduces to 0, 1, 0, 1, minus 3, 0, 1, 3, minus 8, 0, 5, minus 2, 11. which becomes 1, 0, 1, minus 3, 0, 1, 3, minus 8, 0, 0, minus 17, 51. And last but not least, we get 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, minus 3, so that M2, 1 equals 0, M2, 2 equals 1, and B2 equals minus 3. That gives us M equal to 1, 0, 0, 1, which is interesting, the identity. And B equal to 2 minus 3. Last but not least, we'll do one more example. Let's get our first matrix 0, 2, 1, 2, 2, 1, minus 4, minus 2, 1. Multiply that by M1, 1, M1, 2, B1. Setting that equal to 5 halves, 7 halves, minus 7 halves. And then our second matrix, 0, 2, 1, 2, 2, 1, minus 4, minus 2, 1, same as that, minus, but multiplied by M2, 1, M2, 2, B2, and set equal to minus 1, 3, 9, or minus 9. Almost lost my negative. Can't have that. So the first augmented matrix reduces to 1, 1 half, 7 fourths, 0, 2, 1, 5 halves, 0, 2, 3, 7 halves. We keep going, get a leader 1 in the second row, 1, 0, 0 half, 0, 1 half, 5 fourths, 0, 0, 2, 1, which becomes 1, 0, 0, half, 0, 1, 0, 1, 0, 0, 1, half, giving us M1, 1 equal to half, M1, 2 equal to 1, and B1 equal to a half. For the second augmented matrix, we get 1, 1 half, 3 halves, 0, 2, 1, minus 1, 0, 2, 3, minus 3, which becomes 1, 0, 0, 2, 0, 1 half, minus half, 0, 0, 2, minus 2. And we get 1, 0, 0, 2, 0, 1, 0, 0, 0, 0, 1, minus 1. So that M2, 1 equals 2, M2, 2 equals 0, and B2 equals minus 1. Okay, so we have M equals half 1, 2, 0, and B equals half minus 1.